Okay. So, hello everybody. I am Tommaso Dal Sasso. I am from the reviewing group from the University of Lugano, and I want to talk to you about the way we talk and deal with bug reports. Now, I guess most of you know what this is and how a bug report looks like. So, well, we usually have some metadata that describe our problem, and then we usually have a big chunk of text that contains all the information we are interested in and that we have to deal with. Now, we have been using this approach since forever, and well, it has worked so far because mostly it's really flexible. Independently from the language, we can describe different problems and solutions without worrying really about what we are dealing with. So we can write a single issue tracking system and use it for all the languages. However, this approach has several problems. The first of all is that you have to deal with text. And when you deal with text, you have to actually read what you're looking at. And that's required time, because you have to understand and interpret what you are reading. You have to build a mental model of what's written inside. And also, it's possible that since reporters are not often that skilled in the context of the program, of the software program, bug reports might contain errors or be inaccurate or incomplete. Also, since we are dealing with text, it means that we don't have a model of what we are using. We don't know exactly what's the data contained. We have to usually fall back to techniques like text mining or detection of features or names. And since we don't have a model, it means that also we don't have a common interface to talk with these bugs. And since we don't have an interface, we also cannot automate the way we talk and deal with bug reports. We are missing a sure way to write a program that says, go through all the bug reports and do something with that. Now, if you look a little bit closer, you can see that, well, in this description of a bug report, there is one chunk of text, but actually there are different elements. For example, there is an actual piece of text, a description of the user that submitted the bug report, and then you have a stack trace, which is machine-generated code that got pasted inside as a piece of text inside the description. And then there can be several other elements like stack traces, for this is stack trace, like patches or updates from the continuous integration server that says that a build failed or things like that. So we have several types of data inside an issue tracking system. And also here, if you look closer, for example, here you have a reference to a specific version of Pharo, in this case, that is an actual information that means something, but that here, flattened out in text, lost its context. So basically, when we are using text to describe bug reports, we are gaining a lot of flexibility in describing our problems, but we are losing the context of our data. And therefore, we lose data about our data. So to try to mitigate this effect, I try to collect more data about the context of an error, and to reduce the errors introduced by the users that were submitting bug reports. We presented a couple of years ago a ShoreLine reporter, which is a tool that inside Pharo that is shipped with Pharo, so that when a user gets an error, gets an exception, you can select the report button, have a report of what is sending and decide to send it to our server for collection. So in this time we collected a bunch of data that we used to build several visualizations or tools to try to use statistical approaches to understand how the code works, which are the classes that are most error prone, or to build tools to analyze the history of a system from an archaeological point of view. We also prototyped a web application where users could navigate through these stack traces and read them. However, the more we dealt with this data, the more we realized that we were missing something. We are missing something. A stack trace is useful because it gives you some additional context, reliable context about an error, but it only brings you so far. It's not really well, it tells you what is happening, but you're missing a lot of data that can be useful for the developer to further understand the problem. So with this idea in mind, we built the next iteration of ShoreLine that I'm going to show you in a while. So when a user gets an error, for example, it sends an unknown message to a class, it gets the usual exception where it can always press the report button. But this time it gets a window with some additional data. For example, you have the title of the data you are reporting that is auto-generated from the name of the exception, and that can be changed. We have a description box where the user can enter a description of what is happening. And also you have a set of items that can be checked or unchecked to collect additional data. For example, in this case, you can decide to include the version of the system, which of course is useful. You can include the name of the author, your name, or you might not include it if you want to remain anonymous, or include a stack trace if you think you can give it, or if you want to avoid it for privacy reasons, you can not do that. So let me quickly show you. So user items a playground, we get the method. We execute it, we click report, and we get our window. We modify the title and say as of 2016, and say there was a problem with the unknown method. So we send it, we select the items that we want to collect, and we send it, and this information gets stored. But of course, we are only collecting really basic information. We might be interested in much more information about our system. So we built ShoreLine to I think we got kind of screwed. Well, nice.
Did you zoom out?
Okay. Okay, so we built ShoreLine to be explicitly extensible with additional data. So if you want to collect additional data from the system when you're getting an exception, all you have to do is to extend your collector class and implement 3 methods. So let's say, for example, that we want to Okay? Yeah. So we want to collect another type of data. Let's say, for example, just for the sake of the demo, we want to collect the number of classes in the whole system. Of course, it can be much more interesting data, but in this case it will work. So we extend our SL collector and we create SL number of classes. And we extend our free method extract from, that is how the data is extracted. So in this case we can say the size of all the classes in the system. Says, yep. And then we define two other methods. The description method, which is a human readable description of what the data collected is. So we say here the number of methods in the system. And another method tag, which is the machine readable name. Okay. So now we have defined our new type of data that we want to collect. And so when we want to report a new type of data, we get a new item that we are collecting. So why is that? Well, if you think about traditional issue tracking systems, they provide a way for users and developers to communicate, but they lack the essential information of the specific context where the error was generated. So we are missing domain-specific information about our code. Let's think, for example, about Rosal. If a user gets an exception while he's coding a Rosal visualization, maybe Alex, who gets the exception, might be interested in elements specific to Rosal. For example, how many nodes were in the visualization? Is it a memory problem or something else? Think about Petit Parser. If you get an exception during using Petit Parser, Jan might be interested in getting the input string to see what went wrong. Or, for example, with Voyage, you might want to see the method description of the object, or maybe with MetaCello, you might be interested in see the actual configuration of. So you can get additional data that describe your the context of the error that might help the developers. However, if we would just collect this data and put it back in a standard flat piece of text, we would be at the starting point again. So to be able to deal with this data in a more effective way, we defined a new model for storing this data. So instead of saving a bug report as a single piece of text, we split it, all the components that form a single bug report. For example, we have the metadata of a bug report, then we have some comments. A user added a comment, another user replied to that, and then somebody submitted a stack trace, and then a patch was applied, and maybe the continuous integration server added the notification that the build was failed, or things like that. So in this way, we are able to isolate the single elements that compose a bug report and deal with them separately to get and use a specific language for each piece. So if I'm dealing with a piece of text, I know I'm dealing with text. If I have a stack trace, I know that it has a certain structure that I can leverage to perform different analysis. But if you think for a while, you can see that a single element is not necessarily limited to a single bug report. For example, if I get a stack trace might be relevant to several bug reports, or if I submit a patch, this patch might influence different bug reports that contain that class in the system. So we actually model the possibility to connect together different pieces of information to create bug reports that are not monolithic and linear entities, but that actually form a network of information, with of course the possibility to model a single bug report with backward compatibility, because otherwise you would get lost inside the sea of data. But we focused our model on each single piece, and we call these pieces shards. So each shard knows its context. So a shard is either a comment or a stack trace or a patch. And you know what kind of data is that, so you can deal with that separately. Each shard can be linked to other shards, so you create a network of information that you can browse and navigate and search for other relevant information. And also, many linked shards form a stream of information that represent a bug report. Now, this allows us to talk with bug reports, because you're not dealing with that text anymore, we are talking with objects. And since, well, we have bug reports that are object, we have events that are object, and also link might be objects, because, of course, a reply to a comment is different from the stack trace that might be relevant. So we want to diversify also the kind of links that we have between a piece of information. But the more important thing is that we can now inspect and navigate our data in a more structured way. So for a super quick demo, so we have our bug reports and our repository. I can, of course, build a simple browser to see all the bug reports that I have stored, including the one that I have submitted before. But not limited to that, I can also build an interface that, well, some classes, an API to deal with these classes, so I can interrogate our database to get all the relevant bug reports. And this also means that I can integrate this data inside the tools that we already have in our image. For example, if I inspect the class string, I can get a tab with the bug reports relevant to the string, and I can investigate, and I can select a bug report and inspect a bug report inside our tools. So we are able to talk with our bug database without leaving the image. Now, having such an approach and a way to talk with bug reports is important because we are keeping the context of our data. And since we have the context, we also have the structure of our data. We know how to deal with that. So that allows us to perform a lot of automatic analysis that are more reliable and do not have to rely on techniques like text mining or infer the entities. So this allows us to have more expressive power and investigate our data in a more deep way. To talk about the architecture of ShoreLine, how this is implemented, well, we have our server that stores the data in a Voyage database and uses NeoJSON for representing the data in JSON. And we use Teapot to perform the REST calls. In the middle, we built a connector to access this data without having to deal with REST calls. So you can ask for the reports pertaining to a certain class, as you've seen in the demo. You've seen the demo. And you also get the data that are already paged, so you get chunks of bug reports, and you can ask for more bug reports using a streaming interface. And finally, you have the clients like the ShoreLine class or the browsers and other tools that you can use to investigate this data. Now, this also allows us to do specific actions. Like, for example, think that you're browsing a bug report and you are viewing a stack trace, a serialized stack trace. You can add a button and click it, and the system automatically downloads an image and imports the stack trace, and you get, with a click, an image with a stack trace that you were investigating, or with a patch. Or maybe a user submits a patch, and the system can automatically check all the relevant bug reports that include that class to start other tests and see if the problem solved different bugs. So we built and modeled ShoreLine around some basic principles. The first one is that it has to be extensible, so every user can define, you have seen with the class, the data that he wants to collect to allow for domain-specific information to collect. It is privacy-friendly, so if a user doesn't want to submit some information, he can just opt out and click the items and do not send that information. And in a way, we can say it's kind of business-friendly in the sense that every organization can install its own version, specify its own set of interesting data, and have this data available to itself without going for public data. So what's next in our view? Well, to see how ShoreLine is evolving, we have to consider two main points of view. What is already there and what is not there yet. What is already there is basically the corpus of bug reports that already exist and that we have to interact with. So, well, for Pharo is mainly fog bugs. So we built an importer to import data from the existing Pharo issue tracker of Pharo, and we have to refine that to select the specific information that there is inside and break it into the several shards. And also we have to export the data, so if a user submits a new bug report, it would be cool to have this submitted back to the issue tracker to not lose track of this data. And for what is not there yet, well, we built our model and a browser to visualize the data we collect, but we are still missing some critical features of an issue tracking system, mostly normal management of issue tracking system, and for example, assigning a bug report to a user. So we have, in the short time, we will implement that. And also things like authentication. For the moment, I'm using the GitHub authentication to not have to store passwords, but we have to integrate this piece in the browser. So the short-term plans is to release a stable version in the next few weeks to allow people to experiment with that, fix the navigation with the report browser, and improve the integration with Fogbugs to have a free exchange of data between the two systems. And also, since we're dealing with structured data, we can try some automatic approaches, for example, finding relevant stack traces and proposing them to the users when browsing a bug report using automatic techniques. So to wrap up, we have seen that current issue tracking system proposes the data in a flat fashion, like in a dead piece of text, and we are missing the context where this data originated. We proposed ShoreLine, which is an issue tracking system that leverages domain-specific elements to assist developers while reading bug reports. We have seen the model, a new model to describe a bug report, which is not a single piece of text, but several chunks that compose the report. And we have